Okay. Thanks everyone for coming. Thanks to the organizer for inviting me to this beautiful place. Still haven't gone to the Calanques. I must be getting old. Okay. So what are we talking about? Let me start with an open problem, which is still open. Problem is very easy to state. You can tell it to any undergraduate. Take sum plus minus xn. Okay, a random polynomial with of degree n, coefficients plus minus 1. Coefficients, you take them 1 or minus 1 with probability half. Independent. What is the probability that this guy is irreducible over Q? Okay, so irreducible means that it cannot be written as a product of two different polynomials with rational coefficients. Okay? And you want to understand, of course, asymptotically as capital N goes to infinity, and the conjecture, which is, as I said, still open, is it goes to 1 as N goes to infinity. Okay? And of course, the whole point here is that we are working over Q, right? Over complex numbers, any polynomial is reducible. There's nothing to ask, right? Any polynomial can be written as a product of linear terms. Over the reals, any polynomial can be written as a product of terms of degree 1 or 2. So the whole point is that we are working over the rationals. Okay? Questions? Answers? Okay. Okay, so let's the question is still open, but there have been some progress. So let me tell you, let's start with a bit of trying to feel the problem, to see what kind of things ways to attack it. So let's call this polynomial R. So, okay, we want to show that it has, with high probability, no factors. So let's start with degree 1 factors. So what's the probability that there exists a rational number such that x minus q divides R? Is this the right order? Whatever. Okay? What?
Usually it's the other way.
Usually it's the other way. Okay. I'm not being particular. Okay, so you still have an infinite many things inside the probability. So there is it's not immediately trivial, but it can be solved quite easily using a combination of an algebraic argument and an analytic argument. So let me tell you what I mean. So the algebraic input is the lemma of Gauss, which says that in this case, I have to take this one down if I want you to see something. So the algebraic input is the lemma of Gauss, which says that in this case, Q has to be an integer. Okay? It's called the monic polynomial. So Gauss lemma, which is not difficult, just playing around with divisors, saying that Q has to be an integer. So the general formulation is that if you have a root of a polynomial whose top degree is 1, of course you can assume that the top degree is 1 in this case, then its minimal polynomial must also have top degree 1 and integer coefficients. And in this case, of course, you can't get any smaller than degree 1, so x minus q would be the minimal polynomial, so that would imply that q must be integer. Now, the analytic part is that q must be between, the absolute value of q must be between half and 2. Okay, why? Because if the number is 2, then the top coefficient is bigger than the sum of all the rest. If the number is half, then the bottom coefficient is bigger than the sum of all the rest. So that leaves only two possibilities, 1 and -1. Okay, and what's the probability that a random polynomial has 1 as an eigenvalue, as the root? Well, it's the probability that random walks return to 0 after n steps. It's something like 1 over square root n. So we get that the probability that is written in the top board is approximately 1 over square root n, or 0 if you have some even odd issues. Okay, questions so far? That's a full proof, right? Okay. Okay, so since we were so successful, let's try second degree. So again, being divisible by a second degree or any degree polynomial is exactly like having the same roots. You repeat the same argument, you get a bound for a and b. I'm not going to do that in detail. But now you get a nice surprise. Because you see that this estimate, 1 over square root n, which was the correct estimate for 1, for roots of the relevant polynomials, here you get much better estimate. Let's take, for example, the polynomial x squared plus 1. So we are asking, being divisible by x squared plus 1 is exactly like having I as a root. But what does that mean? What is the probability that the random polynomial has I as a root? Now it's a two-dimensional random walk, right? Because because the even ones move only the real part, the odd ones move only the imaginary part, and both has to go to 0. So the probability that x squared divides r is smaller than 1 over n, not square root n. Okay, and again, the smaller is just because of parity issues. Could be 0. If you go to numbers of the unit circle, for example, let me already write it as for example, this guy already decays exponentially. Once you are off the unit circle, it's not so difficult to show. The probability decays exponentially. So all this tempts you to, no, that's not quite what I meant. So all this tempts you to just go possible divisor by possible divisor and check them all. Maybe it will work. And this was done, this approach was carried out by Konyagin in 1999. And he made a serious effort. He certainly held no bars. And what he managed using this approach is to show the following. The probability that there exists a divisor of our random polynomial with degree smaller than n over log n goes to 0. Okay? So the paper is very beautiful. I like it a lot. It uses, if somebody knows what's the Mahler measure, let me write that at least. Buzzwords. Everyone likes buzzwords, right? So if somebody knows what's the Mahler measure of a polynomial, that's great. If you don't, it won't appear again. But that's the main tool that he uses in order to make the estimate works. Questions? I said it won't appear again, so I can't say. Okay. Okay, so let's go to the current millennium. Right, okay, there's a list of co-authors here, but it's not one paper with 4 people, but various papers with various subsets of these people. So, so the first paper I'm going to tell you about is with Leo. So, so here is the theorem. So suppose what Leo and I did was to change the question. Of course, since the question is too difficult, so you change it. So how did we change it? We said, okay, let's take our polynomial. Let this time R be, okay, the top coefficients is, because of Gauss's lemma, it's more convenient to have the top coefficient constant 1. But this is not, this is just the technicality. And let's take all the others. Okay, still IID, still, okay, IID, distribution independent also of, not only of I, but also of N. And suppose Ci are uniform in 1 up to L. Okay. There will be condition on L.
Second sum should go to N minus 1.
Yes, of course. Thank you. And start from 0. Then the probability that R is irreducible over the rationals as usual goes to 1, but there is a condition on L. What is the condition? That there are 4 distinct primes that divide L. So for example, 210. So, right, that's the smallest, that's 2 times 3 times 5 times 7. That's the smallest number which has 4 distinct prime factors. And this is the condition in our theorem. Okay, questions about the formulation? Yes?
Also the other way around, that if it's not divisible by 4 primes.
No, I believe the conjecture. It should be true for arbitrary distributions. Okay, it should be true for arbitrary distributions, arbitrary distribution independent of n, but no, this is just this just follows from the way we prove it, and I'm actually going to sketch for you the proof now, and you'll see how the number of primes comes in. Other questions? Yes?
All the coefficients are positive? Is it going to
No, this is not important. Okay, you'll see in a second. Okay, but there is a slight importance that 0 is excluded. If 0 is included, then it's possible that the polynomial be reducible if just the first coefficient is 0. So you just change the question slightly. So if 0 is allowed, then the probability doesn't go to 1, but to 1 minus the probability that the first coefficient is 0. But that's the only change. Other than that, it doesn't matter. Yes. There have been there will be more results, right? There are other co-authors. I didn't finish my co-author list yet. Okay, so let's prove that, but I'm going to sketch for you a proof. But for simplicity, let's do that with 12 primes rather than 4. It will be slightly easier to prove. Okay, so what does it mean that you take coefficients which are uniform between 1 and L, which is divisible by so and so many primes? It means that if you take R modulo each of these primes, then A, so you get, these are 12 polynomials, you get A, that they are independent, and B, that they are uniformly distributed in the finite field. So R modulo Pi is uniform in the finite field 2 power n. To power n. So it's just the uniform polynomial of degree n, and B, that the different and that they are independent. And this answers some of the questions here, because that's what I'm going to use. So if you take any other set of numbers which are different if I take any complete set of conjugacy classes of this product of 12 primes, the proof will work without 0. The proof will work equally well. Okay. And now, let's see. So let's look at them one at a time. Okay, let's call this guy S. So what is the probability?
Verify independent to be in probabilistic sense.
Yes, yes, yes. So, oh yes. So what is the probability that S has a divisor of degree k? So for now, and this is, sorry, I should say, this is this division here is in FP, not when we started. This divides in FP. Okay. This is an old problem, which has been studied by many people, starting by Erdős, in a sense. And the answer is that it's k2 minus some delta plus O small of 1. And delta, I'm sure everyone guesses here, is equal to 1 minus 1 plus log 2 divided by log 2. If I have time, maybe I'll explain this heuristically, and maybe not. And to save you taking out your calculators, this is 0.086 something. Okay? So okay, maybe I'll discuss this a little bit more, but let's finish the proof. Okay. So, what is the probability that R has a divisor of degree exactly k? This means if R has a divisor of degree exactly k, then this divisor should go through all moduli. So it's smaller or equal the probability that all these guys have a divisor modulo P. So the probability that R has a divisor, and this now is in Z, or in Z or Q or whatever, of degree k is smaller or equal than k to minus 12 delta plus O small. But 12 delta is bigger than 1. Then I can sum them. And for small k, use so I can sum them for large k, and for small k, I use Konyagin's results. That's the end of the proof. Questions? Okay, so I will what is going on? Okay. So delta, first of all, delta appears in 3 different places, and this is a bit related to what was in Alice's the previous talk of Alice's talk, that of relations between numbers, polynomials, and permutations. So delta appears in 3 different settings, and let me start with that. And I don't know about heuristics, but at least I want to. Where's the? Here's the race. So it's the probability, and this was the first one that was proved by Erdős already in 1960, the probability that a random number, okay, let me copy that, otherwise I make a mess. Okay, so you take the probability that n is the random integer in some large interval. It doesn't matter which interval you take, as long as it's bigger than the probability that there exists a k between, yeah, maybe I shouldn't, I want to keep, okay, so let's call that L. There exists an L between 2 to the k and 2 to the k minus 1 that divides n. This is equal to k 2 minus delta plus O small f1 with the same delta. This is the first result of this sort that was proved, if I remember correctly, yeah, Erdos 1960. So this is Erdos. And then the polynomial version is just using one of these, okay, basically standard translation mechanism. This is exactly the result that I've already stated over there. Over there. And the third one is for permutations. And then this relation between integers and permutation was mentioned in Elise's talk. So this is the probability that if sigma is a random permutation, then there exists some invariant subset of size k. Okay, so is this clear? There are three formulations. One formulation for integers. Of course, for integers, everything has to be. There is a power. When you translate from polynomials to integers, there's always a power. So you take the divisor, not equal to k, but not a polynomial of degree k becomes a number between 2 to k minus 1 and 2 to k. But the polynomials and the permutations are more similar. This will be in the next time you invite me. So you have some. Okay, any further questions? Okay. Okay, so I think maybe I'll go further because we have many interesting things other than the delta. Okay, but let me just tell you who proved that. So the permutation version was proved by simultaneously by two teams. One is Pimentel, Perez, and Rivin, and the other is Eberhard, Ford, and Green. Okay, but I won't write so many names. Okay. So let's. So this was this result is from 2020. Let's move a little bit further. Let me tell you now about the result of Brouillard and Variou. Brouillard and Variou. Okay, also from 3 years ago, 4 years ago, something like that. So what did they prove? They proved that if Xi is any distribution on the coefficients, and you construct R as there, then the probability that R is irreducible over the rationals goes to 1 as the degree goes to infinity for arbitrary distributions. Okay, but I just told you that this question is open, so I must be missing, I must be hiding something. What I'm hiding is assuming the generalized Riemann hypothesis. Okay, so you're seeing we are getting deeper and deeper into number theory here. The generalized Riemann hypothesis is relevant here. I mean, okay, now a short interlude for people who know something about that. There is a generalized Riemann hypothesis for L function. That's not generalized enough. So you need the generalized Riemann hypothesis for Dedekind zeta functions. Let me stop there. I think maybe I'll tell you a bit about what's the relation, because this looks a bit ridiculous to keep it this way. Okay, so let me since I have an hour, right? So let me tell you a little bit how the generalized Riemann hypothesis goes into this. So the idea of Boolean value is not to, like in the paper that I proved that. What did they do? I don't think that's the board I had in mind, but okay, whatever. These numbers should correspond to to the height, not to the depth. It would be much less confusing. Okay. Okay. So instead of reducing modulo 4 or 12 primes, like in the proofs we just show, Boolean and value, they reduce modulo many primes, but they don't check the entire divisor structure like we did. They only check the number of roots. So if you want, let's define some auxiliary function. This is, by the way, a completely my view of what they do, okay? We won't find it in the paper. They probably won't agree, but still I'm going to say it anyway. Okay, so let's define the following function. This is a product over all primes of what? Of 1 minus the number of x's in the finite field such that r of x is equal to 0. Divided by p to the s and to minus 1, whatever, that's not important. Okay, so this is just some definition, but let me, maybe I should have used the water eraser. Okay, I'll read it in case it's not readable. Okay, you take some prime, you look at the number of roots of our random polynomials modulo this prime, and you just put it where you would have 1 in the zeta function, right? Like the Euler product formula for the zeta function is just 1 minus 1 over p to the s, and you just replace 1 with the number of roots. Okay? Is the definition of this function clear? Okay. Now, what they show is that this number is on average, and this is a 1. For p, they go very far. Somehow, the further you go, you would get a stronger result. If you could go sufficiently far, you wouldn't need the generalized Riemann hypothesis. But they managed to go all the way to e to the, okay, let's say s to power 0.99. I'm cheating slightly, but not too much. Okay? So they managed to get to p, and they managed to show, and this is by a probabilistic argument, right? You have a random polynomial, so you want to know what's the expected number of roots. You just put a number in it. You see what's the probability that, and they managed to show that up to here you have sufficiently fast mixing of this process to be able to estimate that the number of roots, since you have p different values that can be a root, and each one has probability. If you're mixed, each one would have probability 1 over p to be a root, then it should be 1. And they managed to pull that all the way to the e to the s.
How does s relate to the numerator?
I didn't mean s, I meant n. Thank you. S will come very soon. That was the question, yes? Okay. Okay, and this means that they can show that eta of s behaves like the usual Riemann zeta function. The Riemann zeta function has a single pole. So this means that it's something like 1 over s, but not all the way to 0, which is exactly the problem. For s, for example, being something like 1 over or maybe 1 over n to the power 0.99 or something like that. Okay? Now, here comes okay, at some point you understand that some algebraic number theory should come in. The point is that this is a product of functions, of zeta functions. One for every divisor of R. So if you would have 2 or more divisors, then this product, each of them would have a simple pole at 1, then the product should have a triple pole at 1, which would contradict this. Unless these zeta functions have a 0 so close to the pole that it effectively cancels it. Okay? So that's how Riemann hypothesis comes in. You don't actually need that there are no zeros in the entire critical line strip. You only need that there are no zeros which are very close to 1. And of course, on the bad side, because on the good side, you know that there are no zeros. Okay, so I know that's not a proof, and that all you can get from it is a bit of a gist how the Riemann hypothesis goes in, but at least it's something. Okay? Not too technical questions? Yes?
The zero, you need that the zeros are, there are no zeros at the right of s equals 1 or at the left?
On the left. Did I say right? On the left, yeah, because on the right you know that there are no zeros.
Okay.
Right, but the critical strip for zeta functions starts at 1, is between 0 and 1, right? In the real part between 0 and 1, right? That's the, right? For this classical Riemann zeta function, right? The sum converges in the entire, on the right of 1 plus IR. Then you can, and then you have, and then you extend it to 1, 0, and then there is this functional equation that Riemann is perhaps Riemann's most important discovery that allows to invert it and do an analytic continuation to the entire plane, and also to conclude from the fact that you have no zeros here that you have no zeros here. And then the only question that remains is whether you have zeros in this strip. Right? That's also for the classical zeta function, and it extends also to the Dedekind zeta functions that appear here. Does that answer the question?
Yes, yes.
Okay, any further questions? Okay, so now you are all experts in algebraic number theory, so let's go on. Still have plenty of time. Okay, so we, in a way, we leave the Riemann hypothesis, though not completely. Okay, so this is T2, right? Right, okay, and that would be T3. Okay. So now we are getting to results which are, well, not yet published, though certainly on the archives for a while. And the next result that I want to tell you about is with Leo and Dimitris. Dimitris Koukoulopoulos for Omer. And what we tried was to remove the arithmetic restrictions in the theorem with Leo and to replace them by analytic. Maybe I'll just modify the formulation here. Okay? So what we did, it has the same formulation. You take a random polynomial with coefficients xi, and they are, say, uniform between 1 and L. But you replace the arithmetic restrictions that you had, that we had before, with simply L sufficiently large. Okay, and for me, that's not what I'm going to say now is not important, but some people like that, because I'm not a number theorist, so I don't care about actual numbers, but sufficiently large is 35. And okay, and this is, and the idea is basically is somehow easy to state, but very difficult to pull through. And the idea is as follows. Okay, so you take L sufficiently large, million. Okay, so modulo million, and you still take the modulo 2, 3, 5, and 7. You still look at these four polynomials, which are in 4 different finite fields. Okay, they are not uniform, but they are approximately uniform. They are not independent, but they are approximately independent. So probably something should work, right? So and yes, and the answer is actually it actually works. Let's do again. Did I already erase that? I did. Okay, but let's do a numerical example, right? Instead of working with polynomials, which is a bit confusing, let's see how this question translates to numbers. Everyone likes numbers, right? So the analogous question, okay, okay, I see I already erased everything that I need, but okay. So we want to understand what's the probability that our random polynomial has a factor of a given, a specific polynomial as a factor. So the analogous thing would be to ask what's the probability that a random number would have a specific number as a factor. And the analogy of having not uniform coefficients would be having the random numbers having not uniform digits. Okay, and this is a problem that was, okay, so you take, for example, n is random integer, non-uniform digits. Digits are distributed by some xi. You choose whatever xi that you like. For example, you don't like the digit 7, so you take the distribution which takes, which gives you 1/9 possibility for all digits except 7 and 0 for digit 7, or whatever distribution you like. And you want to say what's the probability that a given number divides n, or okay, it's not written, or that once you have that, you can start from these to construct more sophisticated events, like having a divisor be in an interval, or having so and so many divisors in an interval, and so on. You want to somehow develop the entire divisibility theory, and you start from the most basic question. What's the probability that a fixed number divides a random integer with non-uniform digits? Okay. What would Bourgain do? He would do Fourier transform. Okay. So certainly this is equal to 1/k. Sum of you do discrete Fourier transform modulo k, and yeah, did I use I? Let's write it this way. Right, if you have a distribution, right, the number modulo k is a random variable modulo k, which is the sum of variables which are not uniform, but they're independent. And so, for any function, the indicator at 1 is just the sum over all the Fourier transform and of all the Fourier coefficients. And the Fourier coefficients are products because the digits are still independent. Okay, I didn't put it here, but okay, that's not it. Okay, right now I just wrote that the probability is the sum of the Fourier coefficients, but the Fourier coefficients are themselves products. And then if you have some control on how these products, these are product, the Fourier transform of every specific digit is 1 at 0, but and smaller than 1 on others, and then if you have some reasonable control, you can show that the product goes to 0 and estimate everything. So I'm certainly not going to do that. How much time do I have? Okay, almost nothing. So we'll have to skip the large sieve. But and also all the analogies and all the analogies between integers and polynomial. What is the Fourier transform of polynomials? That's a very nice theory, but we'll skip all that. And I think from the result of this paper with Dimitris, which is quite long, I will only state one lemma, and you'll have to suffice with that. Okay, so lemma. So you take, okay, maybe I will write the formula from the middle to the, from the center to the out. Okay, maybe not. So you look at the probability that our random polynomial is equal to some b modulo d. Okay, b and d are both polynomials. Okay, now this, if it were uniform, then this would be more or less like 1 over p deg b. So you remove that, which is exactly like removing the zeroth coefficients, Fourier coefficients in the numerical example. You take maximum over b and sum over d. So this is a huge sum, huge over exponentially many things, right? And over all d of degree smaller than n half. And this is still quite a small number. So that's somehow the main lemma of the paper. Okay, except, of course, the way I stated it, there is a mistake. Why? Because this cannot possibly hold if the polynomial d is just the polynomial x. Right? Because if you take modulo x, then you just get the lowest coefficient. Right? So you have to remove that. So basically, let's remove everything that is divisible by x. And that's now the correct formulation. Okay, so again, so there is the paper is somehow, I put you, the only thing I gave from the paper is the middle formula. So you spend like 30 pages proving this formula and then 30 pages concluding from this formula the result. So, and this you prove using analogs of polynomial analogs of this Fourier expansion, the polynomial analogs of the large sieve inequality, if somebody knows what it is. If you don't, you are a happier man. And you finally get to this remarkable formula which tells you that, that the deviation from what would be uniform are very small even after summing. Okay, and in fact we do that for 4 primes simultaneously. So what you do is you actually use that for d, which are a vector of 4 polynomials, each one in one finite field, and b, which is a vector of 4 polynomials modulo d, each one modulo the appropriate. Okay, questions about the formulation of the lemma or the theorem? I'm almost done, so I'm also almost done with time, but so don't hesitate to ask questions because I'm only going to tell you about one small, fun result in the end. Okay? Okay, so one very, very recent result just from last month. No, I'm exaggerating, but basically from 2 or 3 months ago. And this is with Leo and David Hocken. So what we just returned to, okay, not plus minus 1, but the second, but an equally classical problem of just 0, 1. And here is the theorem. I will be able to write, right? Yeah, okay. Theorem. Now you take C in 0, 1. Uniform. Then we still can prove that the limit is 1, but we can at least prove that this limit superior is 1. Okay, so this is just from, we put it on the archive. Did we already? Yeah, we already put it on the archive. With Leo and David, and this uses really, no, 0, 1. This result is very particular to 0, 1, and what we are using here is, maybe it's minus 1, 1. No, yeah, it's minus 1, 1. What am I saying? Minus 1, 1. I was just going to say, and what we are using is, and then, okay, that's it. Yeah, minus 1, 1. And what we are using is that a minus 1, 1 modulo 2, you always get the same polynomial. Right? And this polynomial has some divisibility properties which are known. It's basically a cyclotomic polynomial. The divisibility is not like this. Okay, first you divide into cyclotomic polynomials in over Q, but after that you also have to divide further into cyclotomic polynomials modulo Z, modulo 2, which are somehow could be smaller, but they are completely known, and that reduces the number of possibilities you have when you push that into the big analytic mechanism, which we did with Lior and Dimitris, and you can eventually get a proof from that. But it's only lim sup because you need some properties of the cyclotomic polynomials, which some of them are only conjectured, but so if you want an actual proof and not something that depends on some hypothesis, then for example, it works if you take the degree to be 11 to the k minus 1. So for example, over this subsequence, you can pull an argument. That's what I wanted to tell you.